go through some of the lessons in the volume 4 of the curriculum, the latest volume of the Fulldome curriculum that you should be receiving when you get your updated preview suite, hopefully within, I would guess, 3 to 4 weeks. So what I'll do is some of it you've seen parts of already. So I'm going to go through, or I'm going to share my screen. If you have any questions, don't be afraid to interrupt. I won't have any answers, but you can interrupt. So I'm going to share my screen. So you should all see my render box screen, my ATM4 scripts, and the showlets that I have out, and I've got on the tab for the mini lessons. So I've been experimenting with some constellation files, which I'm going to include in volume 4 as I get them made. So I just want to do a couple of them to show you what I mean by constellations in depth. Sometimes you want to go into a constellation in a little bit more detail than others. Rather than just pointing them out, you might want to show some deep sky objects. And sometimes people will ask you for a particular constellation that you're not exactly ready to do that with. If you already have a couple of dozen of these made, you could just pull them in as subroutines in ATM4 through a showlet, as I just did with Orion in depth. So let me run this, show you what I mean by this. So I've got a typical January sky. And as I go through this, what this will do is outline the constellation. And then it names it. Then it puts up its illustration. And then for those who care, it puts up the IAU boundary of it, because you could have that or not. You can just get rid of that if you don't want it. And then the question is, okay, well, what are the bright stars in the constellation that you should know? Where in Orion, it's Betelgeuse or Betelgeuse, however you want to pronounce it. Whoever made it up is dead now, so what difference does it make? The knee star, Rigel. Okay. So now what we're going to do is we're going to aim our telescope, we're going to zoom in and take a closer look at the constellation. So this usually, remember, this is the whole dome. So that's why Betelgeuse is upside down. It's actually right side up for the people looking on that side of the room. So we're going to take a look at two objects, two deep sky objects in Orion, M42 and the Horsehead. So we're going to center on M42 and then zoom in with our telescope, get a good picture of the Orion Nebula, the star forming region where stars are being born even as we speak. And that just put the label on in case you're not listening to what I'm saying. Then we zoom back out because we notice this really pretty emission nebula, H alpha emission in the Horsehead Nebula. So we'll center on that puppy and zoom in on that. And then basically the subroutine ends and we zoom back to the original sky. So in that little routine, that's kind of a cool thing. So let me do Taurus to show you. It has this exact same format. So once you've got one of these made, you can use that as a template to make any others that you want. So there's Taurus, the outline, the label, the illustration, the IAU boundaries, get rid of those. The only bright star in Taurus that people care about is Aldebaran, eye of the bull. Now we're going to center on a star in Taurus so we can zoom in and take a closer look at the region, see what's in there. There he is. So of course the most obvious thing to look at is the Subaru. So we'll zoom in on that. Because we call it the Pleiades, but the Japanese know the real name. And then the other most famous deep sky object in Taurus is near the horn. and that's M1, the supernova remnant, Crab Nebula. So Starry Night is a beautiful means for showing your people all these beautiful objects that are embedded in Starry Night. And I just find it zooming in and moving around with the center command is a very powerful way of doing that. So my plan is to make about, I'd say 20 or 30 of these of the most prominent constellations, and include that in eventually with volume 4. That's my plan, if I can get Q capture to work again. Okay, the Hubble Ultra Deep Field, I think I've shown you that already. Does anybody want to see that again? Maybe some people didn't see it, I don't know. Did everybody see this?
Please show it.
Who's Leslie?
Yeah, that's me.
Did you want to see it?
I would love to if there's time.
There's plenty of time. We have 4 hours here, so you know, we got lots of time.
Let's hope not.
Yeah, you and me both. So the Hubble Ultra Deep Field was taken by the Hubble telescope, I think it was about 10 years ago. I forget the exact date. It doesn't matter. And it's a beautiful thing. Let me just show you. This is, again, a dome view. If I had an audience in the dome. So I would put up a picture of it in the dome, and that would be very impressive. And remember, I have concentric seating, so I have the picture on both sides. Since that's not the case right now, let me put up a flat image of it so that you guys can see it and be more impressed with it. And of course, it doesn't show up because I picked the wrong one. So give me a second. I have the one for the dome, not the one for preview suite. So let me fix that. This has a nice, pretty picture on it. So in the actual dome show, I wouldn't have this picture projected, but this is nice so that you can see it. And I had my wife this morning count the galaxies, and she assures me that there's 10,000 in this image. So that is a lot of galaxies. The question becomes, how impressive is that picture if you don't know the scale of it? And the answer is, it really depends on the scale. How much of the sky does that really take up? So let's see where it is in the sky and how big it is. So we start with Orion, our good friend Orion. Dan Zielinski thinks is my favorite constellation. He actually happens to be correct. Eridanus, which is a constellation that's lots of fun for my astronomy students to learn, all of 38 main stars. And then nestled within Eridanus is Fornax. Fornax is where the Hubble Ultra Deep Field was placed, so that you want to make sure you put it in this constellation because nobody knows where it is. Now, it wasn't arbitrarily chosen. It was chosen for a specific reason. Actually, 2 specific reasons. The first reason is that it's almost 90 degrees away from the ecliptic plane. Let me put up the ecliptic coordinates. And so it's not too far from the south ecliptic pole. You say, well, what's the problem? Why can't you be near the ecliptic? Because that's where the zodiacal dust is in the plane of the solar system. And that obscures faint galaxies. So you don't want to be looking through the plane of the solar system. That's part of it, but there's another reason as well. The Milky Way plane. You want to be away from the Milky Way because the closer you're looking to the Milky Way plane, you've got the same problem. The dust and debris in the Milky Way also blocks your view of faint galaxies. So the Hubble Ultra Deep Field was picked so that it was also close to the south galactic pole. So it's in an area of sky which is quite clean of obscuring material, and that's why they picked that obscure region. So now the question is, how big is it? What's the actual scale of the Hubble Ultra Deep Field? So we'll zoom in so we can see it and fill the dome with its magnificence. And so that's impressive, but it's like, well, yeah, but how big is it? Let's compare it to something whose angular size we're familiar with. So we've backed out, so we've got a sky here of about 6 degrees. And let's put the moon up to scale. So you can see, I hope, you can see that the Hubble Ultra Deep Field, which is about 2.4 arc minutes on an edge, the moon's about 31 arc minutes across. So it's roughly a 15th the size of the moon. So that's a very tiny chunk of sky to have 10,000 galaxies in that chunk. That should blow your head apart. If it doesn't, your head's never going to be blown apart. And then we zoom back out. And the other version I have has the number of, calculates the number of stars in the universe. I showed that the other day. So that's the Hubble Ultra Deep Field. And again, that's something cool you can bring up for your audiences. Just, that's a 10-minute presentation that they will enjoy seeing. Okay, next on the hit parade. The winter hexagon. This is Keith Johnson's favorite asterism. The winter hexagon consists of 6 or actually 7 stars in the winter sky that makes, strangely enough, a hexagon, hence the name winter hexagon. One of the few things in astronomy that actually makes sense as far as its nomenclature goes. The winter hexagon was not an asterism that was put into the asterisms file, so I put that in for you. But pedagogically, just throwing up the asterism to me is not the best way to teach this. I've zoomed in for my preview suite audience to the Orion region. And so what I've done is made 7 asterisms that fit this hexagon so we can do it one at a time and teach it to people. So you start at Sirius. If you can't find Sirius in the sky, go back inside. So Sirius, of course, you can find it by following the belt stars to Sirius. If you can't find Orion, you probably get your eyes shut. So what you want to do is draw a line from Sirius to Rigel, the knee star of Orion. That's the first side of the hexagon. The next one goes from Rigel to Aldebaran. You'll notice that Aldebaran is always drawn in a different size font from the other stars. That's a feature. From Aldebaran, we go to Capella in Auriga. From Capella, we're going to go to Castor. And then we're going to cheat and have 7 sides to our 6-sided figure and go to Pollux. Good enough for government work. And then from Pollux to Procyon, and then back to Sirius. And so here's our winter hexagon. It's quite large in the sky. It has, it really encapsulates some of the brightest, most prominent stars in the winter sky, except for our friend Betelgeuse. So that's a great thing to teach your audiences. That will help them find quite a bit in the winter sky, which is my favorite sky, except it's cold. So that's the winter hexagon. Is it 6:30 yet? So the next lesson is something that I keep trying to teach students, and they just don't seem to get the idea. So I asked Clint to put in a new feature in Starry Night, and that's the Earth-Sun line of sight. So here's the Earth, there's the Sun, here's the orbit of the Earth, and here are the zodiacal constellations in the background. So let me turn the Earth-Sun line of sight on. So it's a line that goes from the center of the Earth to the center of the Sun and goes out to infinity and beyond. So that actually is going to define where the ecliptic is. That was not a trivial thing for Clint to figure out how to draw. You try drawing a line out to infinity, see how far you get. That's the genius of Clint Weisbrod. And of course, the sexy thing about this is, the reason I had him draw this is if we advance time, what happens is that end of that line is going to draw out what we call the ecliptic, the plane of the Earth's orbit in the sky. And I'm hoping that as people see this, it's actually going to make sense, perhaps for the first time, as to exactly what the ecliptic is. That it's the apparent path of the sun in the sky as seen by an observer on Earth looking at the sun, who, everybody on Earth knows the Earth doesn't move. And so it looks like the sun's doing all the motion along this line. So I'm hoping that that will help people. Shall I start over again for her? I'll go back and start all over. No? Okay. All right, so let's continue. That's the first part of the lesson. Now we're going to take a look at it from a slightly different point of view. Now that we've seen it from that point of view, here's the inner part of the solar system. Let's go to the plane of the ecliptic. So we've got the Earth here. Okay, I'm going to make things, the body smaller to scale, and then I'm going to just zoom in with the scene so that we're behind the night side of the Earth. This makes sense to most people because there's the sun. So this must be the night side of the Earth. Okay. If the adults don't get that, ask the first graders. They do. Okay, so let's draw in the ecliptic, which of course mimics the Earth's orbit. Let's put in the Earth-Sun line of sight. And now let's put, we're looking at Taurus because it's May. Anybody born in May is a Taurus. Now let's advance time. So we're going to do exactly the same thing we did before, but now we're going to travel with the Earth, behind the Earth, as the Earth orbits the sun. So this is the view that you get from Earth of that previous scene. And I'm hoping people can make that jump to be able to understand that this is really exactly the same thing you just saw, except now we're traveling with the Earth, not watching the Earth orbit the sun. So as the sun enters, it's interesting that because I'm on Zoom, the timing is off. I don't know if you noticed the constellations are coming before. Yes? If you guys weren't here watching, it actually matches pretty closely, but Zoom is making my computer run slower. So that's what's happening here. And that's not a tease. That actually is the case. So you might keep that in mind when you're online. You've got stuff all set up and all of a sudden things don't run it correctly. Your computer is straining. That's what's happening. Okay. Next, let me do this one next. This is kind of fun. This is thanks to Scott Huggins. The Hubble tuning fork was a diagram that Hubble first published in the 1920s as he was studying different types of galaxies. Notice in the background, we're loading, this is better known as a crap load of movies and slides. But your audience isn't going to see that. You're supposed to talk about the original Hubble. This is the original. I stole this from his book. And so he made this diagram. He's got normal spirals here. He was drunk when he drew this one. If you look carefully, he's got the two arms coming from the same part of the nucleus. He's got elliptical or ellipsoidal galaxies here. He's got barred spirals, or as we say in New England, bad spirals here, with the bar coming out of the nucleus. And then you've got these lenticular galaxies called S-zeros here. Now, when Hubble set this up, this diagram he thought was denoting evolution. The galaxies were born as ellipticals. They got to this juncture, and then they either became what he called normal spirals or these bad spirals. Okay, so he thought this was evolutionary. It's not evolutionary at all. We know now it's simply morphological. It's only based on shape. Galaxies don't go from one type to another. The only exception to that rule is when you have galaxies colliding, then they turn into irregular galaxies and they need Pepto-Bismol. So this diagram comes out of the 1920s. So let's go to the 21st century and make a Scott Huggins Hubble tuning fork diagram. So here we have galaxies taken straight out of Starry Night. These are actually videos of three-dimensional galaxies that Scott and Steve and I and Clint made. Let's put the classifications of them on there. And then, of course, the cool part is, since they're videos, we can make them all rotate. So if you look at them carefully, you'll see that they're all rotating around, so you can see the planar nature of them, as opposed to the elliptical. This is actually a galaxy that's spherical, so it looks like he's not rotating. You can see the twinkling of the stars as the E4 as well. They are moving. And the irregular galaxy is moving as well. This is just a really cool 21st century version. And if you let it run long enough, the movies run out and then they die. And that, you can tell the students, that's an indication that eventually the universe comes to an end and they don't have to study anymore.
Hey, Dave, just a comment to address that. I re-edited and made them each about 5.5 to 6 minutes long, but maybe they didn't get to you. The really, really long ones will need to be plugged into the mini lesson.
That's, yeah, Scott, make sure that Brad knows that, okay?
Yeah.
Because he's the one that puts together all the curriculum for the preview suite. But thanks for making those too. You're a hero for doing that.
Oh, well, thank you.
Okay, the next feature I'd like to show you is perhaps my favorite. Yeah, speaking of which. Let me just check something for a minute. People who are old hands at Fulldome know what just happened. Anybody want to yell out what just happened? I got bitten by my own bug. The focus of interest was set differently instead of being at the zenith where it's supposed to be. Okay, so Kepler's second law is something that's not all that intuitive to students and probably to most people. But basically, Kepler's second law was an attempt to explain the different speeds of the planets at different parts of its orbit. This is entirely due to the changing gravitational force between the sun and the planet as it moves. The closer it is in, the harder it's being pulled. Therefore, it accelerates and goes faster. And vice versa, when it's at aphelion furthest away, it slows down. But because of the laws of nature and something called the conservation of angular momentum, Kepler's second law is conserving something. And so what I had Clint design for me was so that you'd have a Kepler second law in real time where you can actually set the size of the sectors in the ellipse. So these sizes are entirely up to you. The colors are up to you, although you're limited to 2 colors. The areas that are being drawn, and I'll stop time in a second. So what's happening here is there's a lot going on here. Theoretically, based on the time that I told it to go from here to here, and that's entirely up to you, you will get an area from a very simple analytical equation. And so that's what this expected area is. These numbers, you're saying, well, yeah, but they're all the same. They're the same as that. Yeah, but these are numerically integrated. This is not from an equation. Clint is actually adding up the area in the curve. The fact that they're the same is basically proving to you that the law of equal areas here is correct. So the more you understand what's going on, the more flabbergasted you should be by it. Okay, this number 0.037 square AUs, this is numerically integrating from a numerical method. This is from an analytical equation. Of course, they're going to agree. You can change the width of these by telling, there's all kinds of things to change. And what I'd like to do is just, I'm going to stop sharing this screen. I'm going to share my pre-flight GUI. I just want to show you the controls that you have. And this should be in your pre-flight. So let's share this screen. lost everybody. Let me share this screen. You should be seeing my preview screen, yes? Okay. So let's
Yes.
just pick, yes, thank you. Let's pick Mercury, since that's the planet we're messing with here. And just right mouse click on it. And if you go down past these things, you'll see Kepler orbit sections. That is specifically how you address this. So let's go into the options. And so this dialog box gives you lots of options, okay? So let's just quick go through them. The time interval, you can put in whatever you want. You can either do it in days or years. Days is typically what you'll use. And if you have no idea what to do, guess what you push? Yeah, push suggest interval, and it will suggest an interval for you that will make pretty segments, okay? And if you don't like that number, you can change it to whatever you want. But if you hit suggest interval, that's usually the one I use. I talked with Clint about that. It's a little more, to figure out that segments on your own is not hard once you get used to it. But if you're not used to it, it's nice to have that in there. How do you draw them? It's interesting when Clint and I talked about this, he thought I just wanted to draw a segment here and a segment there. And I wanted to draw them continuously through the orbit. So we had a miscommunication there. So we put both in. So if you just want to draw one segment of the ellipse, you'd click on one shot. If you want them continuously drawn the way I just demonstrated, then you would hit continuous. Okay, and as far as the output of text, you can include the computed area with it, and it'll draw the areas of each segment. Okay, and this is the expected one. This is from the analytic equation. So if you don't want all that coming up, you can just click those off, and the numbers won't show up. So this is what Scott Huggins would put up because he hates text. He just likes pretty pictures. The section opacity tells you how dense to make the drawing, so you can make it very faint or very thick. And this is an interesting feature. This just happened with this particular version of Preview Suite. The section colors. They're supposed to default to red and blue, but we have a new feature where they're both the same color. Well, if you draw them both the same color, you might as well not draw them at all because you can't tell the difference from one to the other. So to change colors, just click on the color, and then you can pick any color that you want. I don't know what happened to my version. I think it's demon possessed. The remove all, if you hit that, what that will do is take everything off the screen, everything you've just drawn, okay? But if you want this thing to actually draw, you have to click either one shot or off. And then once you've got everything set the way you want it, then you just click this. And now if you run pre-flight, it will actually draw the things the way you want it. If you save a favorite, it'll save all those in the favorite, okay? That's just a rough, I don't want to spend all day doing that, but once you play with it a little bit, you'll see that it's really quite cool. Okay, now I am going to stop sharing this screen.
Numbers are good, Dave.
Yeah, I know, Harold, but Scott doesn't like them. He's very aesthetic. Okay, now I'm going to go back and share the render box screen
No,
again.
us.
I have some more neat orbits to show you, or I could just show everybody's face. Okay, so let's continue. And this, I showed you this before. This is the one-shot deal. If we go to manual motion, it'll draw one segment until I stop the motion. I'm doing this with the pre-flight time controls. Now, if I run time forward again, it draws another one. And it won't draw another one until I stop it and then make it go again. You might say, well, could you do that with alternate stop times in ATM4? And the answer is right now, no. So that's kind of, so if you like to do that, if you want to reproduce what they normally do in a book and draw it at perihelion and aphelion, you can do that with the one-shot deal. You just have to be, you know, you can start in 19, right? Shall I answer that question from Laura? Laura, are you interested that there's the two?
Playing along, and when I did the one shot and
Yeah.
time, I got one segment.
Yes.
You've been illustrating how you can.
Yeah. So if you stop time
Yeah.
and then start time again, it should draw another one. Every time, if you start it, it'll draw one segment, then stop time, then just start time again. It should draw another segment starting where you stopped the planet. Okay?
Yep, it's working. Thank you.
You're welcome.
Dave, I see how Sholets work in your lessons, but
Yeah.
I've got a show that has like 4 sub-shows. Is Sholets going to work in that one?
It can.
Okay.
It
I
can
need
be, you would just have to make a Sholet button for each sub show.
Okay.
If you want to be able to do sub shows individually.
Yeah, I really do.
Yeah, then use that Sholets will work, Harold.
Because 3 of those 4 things are really can be independent shows depending
Exactly.
on what the audience is.
Yeah, and that's what you want to. Sholets is beautiful for that. That's why we put the curriculum into those.
Thank you.
You're welcome. What do I know? Let's do a couple more. This is actually Mars. I like this one because Mars is really the planet that gave early astronomers the biggest headache. This is why Kepler wanted Tycho's data from Mars, because Mars's orbit did not fit circular orbit stuff in the Ptolemaic system. It was the one that was the worst. But of course, it fits an ellipse beautifully. So here's Mars going around in its orbit. The next one is a very extreme one, and that's Halley's Comet. There is a memory limitation with this feature. So if you just let something with a large eccentricity go long enough, what will happen is that eventually, as it starts drawing more and more out here, this one's going to disappear, and then this one's going to disappear, and this one. Okay, so as it gets to a limit of about 30 or something, Clint had to draw a limit, otherwise it'll crash the system because it is a memory hog. And again, if I were showing this to an audience, I probably wouldn't have these texts on to get in the way of the pretty segment. This particular object, I was looking for an asteroid that had a high eccentricity. This is Apollo 1862. Has an eccentricity of 0.56. And the reason it's interesting is it actually intersects the orbit of Venus. So it's one of those few asteroids with a Venus intersecting orbit. But it makes for a beautiful demonstration of Kepler's second law.
Someday, might it hit Venus?
No, I don't think so. I don't think it actually crosses the orbit. It's either below it or above it or something. Or it could be next Tuesday, Harold, but I don't know. I'm pretty sure it's not going to hit. We just had our first thunder, so if I disappear, it was the thunderstorm. Or it could be my wife because she just closed her picture. The next one I'd like to show you is Nereid, which is the highly eccentric 0.76 eccentricity orbit of Neptune. I like this. If you look carefully, can you see Triton going the wrong way? The Triton orbits clockwise instead of counterclockwise as seen from north. But again, you get to see, and I turned the numbers off so that it would be aesthetically pleasing for Scott. It's a very impressive graphic. Fulldome is the only planetarium in the world that can do this, by the way. I just thought I'd mention that. And then the last one, just to show you, so this Kepler's second law will work with any body in starry night except for space missions. So I've gone to an exoplanet. So this is a star, HD 87646A is a star with a couple known exoplanets. So this also works with exoplanets. This guy, I love this. He goes pretty fast. So this is one of the exoplanets in the database of Starry Night. So I just think that's gorgeous. I really, to me, this is the coolest part of the Volume 4 curriculum. And Clint really did a great job in this. You should send him emails and tell him how brilliant he is. I had the idea, but he's this genius and makes it work. The last thing I want to show you is the Copernican method for making a scale model of the solar system. I've saved this for last because this is the most complex thing. This is something that I teach to my college students. High school students could handle this as well. Perhaps upper junior high, because you need to know a little trigonometry. I hate that word because that scares people. Sines and cosines and stuff are really easy if they're taught properly, but they're usually not taught properly, so people freak out. So let me show you what I'm talking about here. Copernicus was the first to make a scale model, a true scale model of the universe. The Ptolemaic system was not to scale. They did not have a scale. The Copernican model had a scale because the sun was at the center. If you knew the distance from the Earth to the sun, that set the scale for all the other orbits. They knew, Copernicus figured out by this method I'm about to show you, all the distances to the planets out to Saturn, which was all they knew, in terms of the Earth's orbital radius. Now he's assuming the orbits are a circle, so that's going to be a problem. He's also, in this model, assuming that things are moving at the same speed, which is also a problem. So for inner planets, the geometry is quite simple. You have the Earth, and I've enlarged these slides. Not everything can you read because some of the text is small. It says 1 AU here. Here's the distance from the sun to, say, Venus. And then you've got this third leg of the triangle here. At this particular position, this is called quadrature, where the angle here between Earth, Venus, and the sun is 90 degrees. It turns out that that occurs when this line of sight is tangent to the circle. And there's a geometrical property that when this angle is 90, that makes this angle as big as it can possibly be. This angle theta is the greatest elongation of the planet. It's the greatest angular distance that the planet appears to be from the sun as seen from the Earth. Okay, so if you were good at geometry, you knew that once you measured this angle, keep measuring it. Once you get it as big as it can be, that means Venus must be at 90 degrees. So if this is 90 and you measure this angle, you obviously know this angle. You know all the angles, so you just need one side and you can get the distance from sun to Venus. Well, we don't know any of the distances. So Copernicus said, well, let's just call the Earth's distance from the sun 1 unit, so I can get this distance exactly in astronomical units by a very simple equation. I just take the sine of this angle to get the opposite side and multiply it times the hypotenuse, which is the distance. Okay? So how do we do that in reality? And the sextant wasn't invented in Copernicus's time. They had to use other instruments. Just thought I'd throw that in. I think the sextant was invented in the 1700s, if I'm not mistaken. So let me just show you the new feature that I had Clint put in. This was before Kepler's orbit thing. I had him, after we did the Earth-Sun line of sight, this was actually easy. I had him put in features where we could draw a line from the Earth to the Sun and from the Sun to each of the planets and put the distances and angles between them, label them all. So basically a sextant built into Starry Night. This, again, no other planetarium program can do this. So we set up the scenario. Here's the angle between the Sun as seen and Venus be seen from the Earth. What I'm going to do is advance time until this angle is a maximum, which occurs, of course, when this angle is 90 degrees. And so that angle for this particular configuration occurs, the greatest elongation angle is 45.9 degrees. So if I plug that into the equation we just came up with, it should be 1 AU times the sine of that, which comes out to 0.72 AUs. Is that correct? Well, we can put up the actual number at this particular configuration, which is 0.73 AUs, and that's more than good enough for government work. Now that works beautifully in this case because Venus's orbit is the closest to a circle in the solar system. Its eccentricity is 0.00 something. Eric would know, I forget. I think it's 0.09, but I forget the exact number. What does this look like though on the Earth? Yeah, if Copernicus was out in space looking at this, that would be easy, but he's stuck on the ground. So let's see how he did it from the ground. So this is the dome view. There's the Sun, and there's Venus. Let's put a few features in here. So there's Venus's orbit. And let's draw in those same lines so that you can actually see them from the Earth. This is the line connecting the Sun to Venus, and what this is the angle between the Sun and Venus. So this is like if you had a sextant, this is the angle that you would read using a sextant.
But he's using a backstaff or a quadrant.
Exactly right. Thank you, Harold. Again, the angle, he wouldn't know this angle, but this is the angle at the planet. We want that to be 90. Now, this is a very hard thing to see in Preview Suite, the way it's set up. So I've zoomed in so you can watch it more carefully. We're going to advance time. I'm advancing time using the rate cube because I'm using annual motion to do this, to try to keep the Sun in the same place as best we can. So as we progress through time, as this angle approaches 90 degrees, you'll notice that the greatest elongation angle will be coming. So this is what it would look like from the Earth. As it gets close to 90, it turns green, just to warn you that it's about to happen. So there's our crescent moon. There's our greatest elongation angle in there. So if I continue this on, this number would actually get smaller. So that's the way it works from the Earth. Okay, so yeah, that's Ducky, right? Thanks, Eric. So how about Mercury? Well, let's try Mercury. Now, this is a very good exercise for your students who can handle this stuff, because what you're going to find is that because of the approximations that are being made here, circular orbits and constant velocity, these numbers are going to start to get bad. That's called real science. So let's set up Mercury. Let's zoom in so we can see him more clearly. And let's watch him get to greatest elongation. And again, you can make the rate of time go faster or slower. I actually had to speed up my rates by a factor of 4 because my desktop runs a lot slower than the render boxes. I don't think Copernicus had cheekbones, Kristen. Anyway, so here is the greatest angle. In this particular configuration is 18.2 degrees. People who know what the average greatest elongation angle of Mercury is will say, hey, wait a minute, that's not even close. You were taught it's 26 or 27 degrees. Right, Todd? Todd Young, you know that, right? Todd Young knows. 18.2, what the heck? Yeah, exactly. So if we calculate the distance from the sun to Mercury based on that angle, it's 0.31 astronomical units. So let me show you. Here's a table for you to memorize. I went through and I actually made this measurement on all these different greatest elongations. This is one of the reasons my wife won't talk to me anymore. This takes some time. Look at all the different greatest elongation angles. So don't worry about all these numbers. If you average them, the predicted size of Mercury's orbit is 0.369 AUs. The actual semi-major axis is 0.387. That's about a 4.5% difference. That's not bad, but you won't get that unless you take the average of a whole bunch of different measurements. So I would ask my students, why? Why is it so far off? What approximations are we making that are showing up here? There are two. Mercury's orbit is highly eccentric, like 0.26, and therefore its speed, its angular speed in the sky, changes all the time. So those two things are going to mess you up, and you're going to get all these different elongation angles depending on in what part of its orbit around the sun you're doing the greatest elongation. Sometimes it'll be closer to perihelion, sometimes at aphelion. You're going to get all these different numbers. So it's a good learning tool. That's why I did all those different cases. You guys still with me? A few people? Thank you, Jamie. Love you, Jamie.
Yes, yes. Still here.
Thank you. Now, that's the inferior planets. The superior planets are a different story. It takes a little bit more ingenuity. What Copernicus did was he timed how long it took for the superior planet, Mars, Jupiter, or Saturn, to go from opposition, when it's on the opposite side of the Earth from the sun. He timed how long it took to get into quadrature, such that, as measured, okay, this angle would be 90 degrees. Now you can't read that, but what that's trying to show is the angle that the planet made from opposition to where it is this angle right in here. The angle that the Earth went from here to here is this angle. What I would like to have is the little angle in here, which is the difference of those two. This angle. Why do I want that? Because if I know that this is 90 and I know this angle, I've got all the angles. And then I can solve this triangle, the distance from Mars, because the angle between the Earth, the sun, and the planet is 90. So I've got this one. This one I can get from the different rate, angular rate, that the Earth is going around. So for example, what's the angular rate of the Earth around the sun? Does anybody know? How many degrees per day is the Earth traveling? Everybody except Eric.
1 close.
degree.
Yeah, do you know why it's 1? Because that's how the degree was defined. You think it's a
Oh,
do you think it's a coincidence that there's 360 degrees in a circle and 365 degrees in a year? That is not a coincidence. So I won't get into that story. That's the Babylonian things. They were into the sexagesimal system, a word I can't talk about with little kids. Anyway, this angle, if I know how fast the Earth is going around, and if I know the period of Mars, I know how long, it's a little over 2 years. I know how fast Mars goes, assuming it's a circle. I know its angular rate. I can measure this by timing how long it took to go from opposition to quadrature. That's the key here. And then I can solve this goofy equation. So it just comes out that if you calculate this angle theta by knowing the difference in time going from opposition to quadrature, if I take the secant or 1 over the cosine of that angle, that gives me the distance to the planet, this distance, in terms of this side of the triangle. So that's how Copernicus did it. He knew the periods of all the planets, and I have another whole lesson on synodic period to sidereal period, a whole bunch of lessons. So he was the first one to actually untangle this. And so if you assume that it's 360 degrees in a circle, you can calculate how many degrees per day for each planet. I put Pluto in because I feel sorry for him. So we know that number, even though that number is an approximation. Let me just go through just a couple to show you how this works. So from outer space, we've got the Earth and Jupiter in opposition. What I'd have my students do is write down the date of that, okay? So the Julian day. And then we speed up time and wait until this angle is 90 degrees, when Jupiter appears to be, instead of 180 degrees away from the sun, appears to be 90 degrees. And we would write down that JD. What does it look like from the ground? Well, from the ground, you have really big letters in the sky like this. Here's Jupiter. And when it's on the meridian at midnight, that's when it's in opposition. Hopefully you guys know that. Yes? Opposition is when the planet is on the opposite side of the Earth from the sun. So if it's on the meridian at midnight, it's opposite the sun. That's how you determine that it's in opposition. So let's draw the line from Jupiter to the sun. There's the angle between them. And then if we advance time, and again, this is an annual motion thing. When this angle between Jupiter and the sun goes to 90, there'll be that quadrature. So there's our friend, the sun. So there it is. And so we'd be able to time there to get the Julian date of that. So here's the numbers. The difference between, right, this is where it started at opposition. This is where it ended at quadrature. It's about almost 90 days. The Earth's angular rate minus Jupiter's angular rate, that's what I want to multiply times the number of days. And that will tell me that angle theta. So taking that angle theta and taking 1 over the cosine of it, the secant of it, gives me this for the distance from the sun to Jupiter. The actual semi-major axis of Jupiter is 5.2. And so we've got a 23% error. And so again, you might say, well, what kind of a crappy method is this? But again, that's not the point. The point is the method is fine. Your assumptions are bad. The orbit is not a circle, and Jupiter does not move at 0.0831 degrees per day every single day. Its motion, because it's an elliptical orbit, it changes its rate, as does the Earth. So you've got all that. That's why you're getting all these errors. And so what you have to do, and of course I've done this for you, is do a few other oppositions to quadratures, get your angle theta, and take an average. So here's the average, 5.47. And that compared to the average semi-major axis is only 5% off. So again, as you have to do in science, you don't just take one measurement, you take a bunch of measurements. And so it's actually a very good method, even with those assumptions. Okay. You guys get the idea? I don't want to bore you to tears.
Do we know if Copernicus did many measurements?
Christy, sorry?
Do we know if Copernicus did a whole bunch of different
I
measurements?
do
and
not
averaged
know.
them?
I do not know. I actually looked into it. I actually looked through Principia, and it was hard to find out exactly what was going on. You know, classics are defined that way. They're books everybody's heard of, but nobody's read. There's a reason for that. The books are intractable. They're very difficult to read. Very difficult to read. So I'm not 100% sure of. He also used past observations by other people as well. That I do know. It's a very complicated thing. So I won't go through the other methods, but Mars and Saturn are also done. They have similar results to Jupiter. They're not, you can't just take one and get a good answer. You need to take a bunch of them. But they all come out to about a 5% error. Okay. So that's volume 4 at the moment.
Very cool.
So I know that the Copernican method thing is fairly advanced. And if you're a college professor or a high school teacher and you've got kids who, you know, actually want to get into this, you could give them, say, okay, we've just done it for Jupiter. Go figure it out for Mars and find out what you do. Go do 20 opposition quadrature pairs of Mars. See what you come out with. And trust me, by the time they've done 4 or 5, they can bang these out in about 3 minutes. And it's, you know, they'll get all these different numbers. And the first couple, they're going to say, well, how do I know when quadrature happens? And what? It's a good exercise to teach them how to figure this stuff out. My goal in a lot of this is to get people to be able to go outside, look at the sky, and actually understand why it is you see what you see. And that is exceptionally rare. Even among planetarian people, be able to go out in the sky and actually understand why it is you see what you see. That's why I invented the planet location class, where you're actually trying to map out where the planets are in the solar system. You know, that to me is one of the most important classes you can have your junior high and high school kids do.
Dave, let me also add that there are many astronomers and astrophysicists that don't know the sky either.
Well,
It's
that's
remarkable.
exactly right, Chris. That's exactly right.
Yeah.
They know their way around. They know their way around the theoretical stuff, but out in the sky, they make stuff up.
Yeah.
Yep.
One of my closest friends, full professor, and he doesn't know the sky.
Yep.
You'd be the first to admit it.
Yeah. Yep. All right. Well, that's all I have for you tonight, and I hope that wasn't boring. I hope that was, like, you know, showing you what's in volume 4. It certainly was a labor of love and an awful lot of work. But eventually, it'll be in your hands and hopefully in your domes. So thanks, guys.
Thank you, Colleen.
Thank you.
Dave, it's wonderful.
Thank you. Thanks for bearing in there. Thank you.
Labor of love, but all our audiences appreciate it, the love.
Oh, yeah.
Well, make sure that you thank Clint, because without Clint, none of this would be going on. Yeah, Clint is the man. So who's running this? Is Brad or Mike? Mike, are you running this?
Brad was host, I think. Yep, Mike maybe host.
I think Brad went to a
Co-hosting.
bar. Oh, there's Brad.
Yeah.
Unless there are questions, we're done. We should go to bed.
Yeah.
It has
Tomorrow
become
morning,
night here, so that would be appropriate.
yeah, tomorrow morning, we have 3 sessions. There's Intro to Layered Earth. There's an introduction to Dr. Bradstreet's Astrophysics software suite. If you haven't seen that before, that's a very interesting set of software. Dave, you want to say anything about that to entice people?
It's 3 pieces of software to try to get across ideas that are extremely difficult to teach in the classroom. On tides, yeah, good luck teaching tides. That's why I invented that program. Even with the program, people yell at me. And epicycles, it's kind of cool to see epicycles, what they actually are, that there actually is some rhyme and reason to why they're set up the way they are. And then Newton's mountain, explaining what an orbit really is. Again, a lot of people, a lot of physics teachers don't understand what an orbit actually is. If you ask your students why things orbit, like why do the planets go around the sun? You know, they'll say things like, well, you know, the other planets hold the Earth away from the sun because they're all pulling on gravity. And that's why it doesn't fall into the sun. To which I always say, well, what's holding Pluto up? And then they just throw things at me. But this Newton's mountain program explains orbits the same way Newton tried to explain them in the late 1700s. People didn't understand Principia, so he published a pamphlet, and this diagram was in that pamphlet. The program actually animates that, and these are programs that are available to you for your side dome, but you have to purchase them. Because we put Dave Steelman and I, my programming colleague and best friend, we spent 7 or 8 years writing these, and perfecting them. So we have to get some money for them.
All right. And then Mike is going to be hosting advanced streaming and online content creation. Mike, want to give a short blurb?
That's real important for me.
It's all about advanced streaming and online content creation, utilizing things like OBS and different sort of software, Zoom and WebEx, and kind of go over that. This is to get you streaming at a production level above where you are right now. That's the intention. So come with questions, come with comments, and we'll try to go over as much as we can in that hour. The one good thing is that we don't have anything in the following hour. So if there's a little bit of bleed over, we do have the ability to take that time. So we won't necessarily have to cut off exactly at 50 minutes.
All right. See everyone in the morning. Have a good night.
Hey, Brad,
Thanks, everybody.
Thanks, everybody.
Question?
what's the advanced user session to be determined?
We'll be updating that tonight. Dan has graciously offered to do a little, basically take you through one of his shows. Dan, you want to say something?
Yeah, they asked, we kind of talked about this morning, and they just said we had a gap, and I said, well, if they want more show production tips, I'll go through one of my shows, play a chapter, say how I did it, and just really go more off of questions than anything else. So yeah, basically show production and ideas and HEM4 programming.
Thanks, Christy. Forgot to mention that. All right, now everybody go take a break from the screen.
Thanks, everybody.
Night, everybody.
Good night.